Balancing chemical reactions that contain polyatomics can be more tricky than just balancing binary ionic compound-based examples. So I'm going to go through a strategy or a trick that can help you balance these much more quickly. 3 of these can be balanced with the strategy, 1 of them can't, and we'll highlight that when we get there. So in the first example, we have iron 2 sulfate reacting with ammonium sulfide in a double replacement reaction. We have iron ions, sulfur ions, oxygen ions, and nitrogen ions, but I'm going to balance this with iron ions, I'm going to balance the sulfate, and I'm going to balance the ammonium and the sulfur. What would make this tricky without this strategy is you have sulfur in sulfate and you have sulfur in sulfide. Okay, but I'm going to treat these sulfurs different. So I'm going to color code the polyatomic ions. So I've got sulfate here. There are no brackets. There's just one sulfate. So I'm going to circle just the sulfate. On the other side, there's also no brackets. So I'm just going to circle the sulfate in red. I have another polyatomic ion in ammonium. Here we've got a bracket and there's 2 of them. But I'm just going to circle in green the ammonium. Okay. We have 2 green circles on the reactant side. And on the product side, we have brackets again, and I'm just going to circle the ammonium, and we have 2 green circles. Okay. Labeling these lets us count things much easier. I'm not going to circle the monoatomic ions, we'll just count those as usual. So now I'm going to count. Iron, we have 1 Fe on this side and 1 Fe on that side, so our iron is balanced. Sulfate, we have 1 red circle here. We have 1 red circle there. Our sulfate is balanced. Next, I move on to the ammonium. My green circles, I have 2 green circles here and 2 green circles here. So the ammonium is balanced. The N's and the H's from ammonium are balanced. Last, we have 1 sulfur and 1 sulfur. So this question was a little bit boring that this was balanced without any coefficients, but I wanted to pick something straightforward to highlight the circling the polyatomics and counting them and not including the numbers outside the brackets. When we move on to the next example, we have nickel chlorate. But when we look to the other side, the polyatomic ion is broken up into chlorine and oxygen. So we're not going to be able to apply this strategy to an example like this. You're going to have to balance each atom individually, just like you would have learned balancing with binary ionic compounds or previously with polyatomics. Moving on to the next example, we have polyatomics that don't break up. We have a single replacement, lithium and magnesium phosphate. So the lithium I'll count like normal, the magnesium I'll count like normal, but here's phosphate. PO4, 3 minus, and I'm just going to circle the phosphate. The 2 outside means we've got 2 phosphates or 2 blue circles, and on the other side there's no brackets around our phosphate because there's just 1 of them. So 2 blue circles, 1 blue circle. And it's just so much faster to count these in groups. When we have the same amount of phosphate on both sides, the P will be balanced and the O will be balanced. Okay. So now that I've labeled this, let's go and balance. I have 1 lithium on this side, 3 on this side, so I'm going to triple my lithium. 3 magnesium here, 3 magnesium on the product side. Phosphate, 2 blue circles, 1 blue circle, so I'm going to have to put a 2 in front, so I have 2 blue circles. Now that did alter my lithium. I'm now 2 times 3, which is 6, so I have to update this number. It is now 6. So the correct coefficients are 6, 1, 2, and 3. Okay. Last example would be as tricky as it would get. we have ammonium, phosphate, and lead nitrate. So we have 3 different polyatomics to keep track of and lots of subscripts. This would be incredibly challenging without this strategy, particularly because we have a nitrogen-based polyatomic ion here and another one there, and counting the nitrogens together would be challenging. So I'll carefully color code. So I'll use red for ammonium. We've got 3 of those. There's a 3 outside the bracket. And on the other side, ammonium has no brackets. There's just 1 of them in that ionic compound. Our phosphate also has no brackets. So there's just 1 of them. And on the other side, there's 4 outside the bracket. So there's going to be 4 blue circles. Okay, I need to be careful not to circle the numbers outside the brackets. 1 more polyatomic ion. We have nitrate. There are 4 nitrates. So we're going to have 4 blue circles. And on this side, no brackets. So there's just 1 nitrate. Okay. And now we can go ahead and start balancing. Okay. The lead, I'm not going to circle because that's just a monoatomic ion. So there's lots of places to start. Some are easier than others. I'm going to start with my blue circles. I've got 4 phosphate on the product side and only 1 here. So I'm going to put a 4 in front. That's going to give me a lot of red circles, a lot of ammonium, IUM. 4 times 3 is 12. So we need 12 red circles on this side. There's no numbers outside the red circle, so there's 1 in each unit. So I'm going to need 12 of these units. This also gives me 12 of my green units or my nitrate. There's 4 of them in each formula unit on my reactant. So I need something and I need to quadruple it. So I need to 3 times the 4 units in my formula unit. So the nitrate's quadrupled in each formula unit. 4 times 3 gives me 12. So my red circles are good, my blue circles, my green circles, and then last, my lead should work out. 3 lead and 3 lead. So this is in fact balanced. The stoichiometric coefficient is a 1. So this would be not impossible, but close to impossible to do fairly fast, I think, without labeling the polyatomics and color coding them. So it can be really handy to have different color pens or coloring pencils when you're balancing, particularly balancing polyatomics. Hopefully this video helped you, and if it does, please consider liking the video or subscribing to the channel.